computation in order to recall the rules that you know about integral computation. And then we will exercise. I'm sorry. Last week I was without my voice, and this week is not so well, but it is okay. Let's begin with some simple integral rules. We have, let me write integrals. Okay. For instance, let's say we have some power of x, and for now we will exercise only indefinite integrals, so without extremal points, but using this type of integral too. And we will do what is, of course, 0. This is why we compute normally in the indefinite case some primitive, and then we add C with this meaning. Okay, so let's begin with some as example. So let's begin with I don't know, 1 over x to the 5th. Okay, so we know that we can rewrite this integral as x to the minus 5, the x. I could have written instead of x, t or y or some other variable. It is the same. This is a dummy variable. That means that it represents only some variable of integration. And as you know, if we derive a power of the variable x, for instance, x to the n, we will have n times x n minus 1. So if we want to do the inverse operation and find a primitive of this function, we have to divide by n in order to obtain this n minus 1. That means if our number is, for instance, 3, we have to add n minus 1 is 4 minus 1. That means that is x to the fourth divided by 4. So the rule is x n. I will write with another letter because normally you have this type of you already have some table for the principal integrals. So that means that, sorry, this this elementary rule is to raise the power by 1 and to divide by the same number. This is the rule that you know. Okay, that means that if we want to compute the primitive of this integral, we have to raise the power by 1. That means minus 5 plus 1, that is minus 4, and divide by minus 4 plus c. Okay, that is minus 1/4 x to the minus 4 plus c. Okay, so this is a very simple type of integral, and normally you can see some exercise like this one where powers of x appear, but you have at first to notice that this is 1/2 as a power, so you have x to the power of 1, so plus 1/2, because the product between the two powers is gives the sum of the exponents, and then you have the integral x 3/2 the x, and then you can compute in the same way. That means you have to divide by 1 plus 3/2. 1 plus 3/2, and x will be to the same power, 1 plus 3/2 plus c. This gives 1 plus 3/2 is 2 halves, 2 plus 3 is 5. That means x to 5/2 divided by 5/2 plus c, and you can write, I don't have space, wait, give me better, and I will write the result in the next blackboard. That is let me write. No, I'm sorry. There is room enough to write dividing by 5/2 means multiplying by its inverse 2/5. So this is the result. So that means every time you have some kind of this kind of integrals and you have only powers of the variable x, it is good to patch these different powers together. As in, for instance, I give you another example. This one. Let's one more, so you don't be afraid of this amount of square roots. What is this? It is the big one, x times, what is there? There is the same as in the previous integral, x times square root of x. This is x to 3/2, okay? But x to 3/2 means that if we apply another square root, it is x to 3/2, then raised to the power of 1/2. Okay? So this is the power of 1/2. That means we have to multiply 3/2 times 1/2. So now we have everything under the first big square root. That means 3/2 times 1/2 is 3/4. And then everything that is inside this square root is x to the power of 1 plus 3/4. So 4/4 plus 3/4 is 7 divided by 4. Okay, what is the next step? The next step is consider again the square root that is raised to the power 1/2, and then something that is raised to another power will be 7 divided by 4 times 1/2. So we will do the next step and the next board. So that means that we'll have x 7/4 times 1/2 in the x equals x to 7/8. Okay. Okay, the big trouble was to be able to consider the right powers, the right exponents. And now this is the same rule as before. That means that we have x to the power 7/8 plus 1, and again on the denominator 7/8 plus 1 plus c. And so we have 1 is 8/8, then is 15 divided by 8, but this is the same as to write 8 above and to write 15 8 plus c. Okay. Okay, I think with the powers it is okay. Okay, so let's perform some other integral. For instance, let's say we have something by part, because something by part that should be, as you know, you have some elementary integrals as exponential function and logarithmic function. Okay, logarithmic function is not an immediate integral because it doesn't exist a primitive of the logarithmic function, but I know that you derived the logarithmic function by writing by part computation. So this is something that is usually used in order to perform integral of logarithmic function. Okay, so let me see what type of integral. First of all, let's write this one, exponential function. Okay, this is important to recall that if you have e to the x derived, the derivative is the same. But if you have e to some more complicated function depending on f, and you want to derive, the derivative of this thing is e to the power of x of the function multiplied by the derivative of f. Okay, that means that somewhere should pop out the derivative of the function that is in the exponent. Okay, that means that we have to take in account to take in account that this is not only x but a function of x. So if we derive e to the minus 2x, we have as a result the derivative of minus 2x, that is minus 2. So it is e to the minus 2x times minus 2. So we want to write minus 2, and in this case, we can perform this computation. We have 3. We should multiply by minus 2 in order to obtain the derivative of e to the minus 2x, but of course we cannot put some inside an integral some number without balancing as a fraction this whole number. That means we are multiplying by 2, by 1, I'm sorry. This is equivalent to 1. That is, if we multiply by 1, the integral doesn't change. So, what is this? As you know, the integral computation is additive and linear. That means we can put together the two terms, minus 2 and e to the minus 2x. I'm sorry, I should have written dx, of course. Dx, okay. So that means that we take this fraction minus 3 half, so it is 3 divided by minus 2, and then we multiply by minus 2 e to the minus 2x in dx, and that will be our computation. So we can put outside this numerical factor and perform the computation. E to x in dx. So we will have minus 3 half that remains outside, and then we have the primitive of the previous function, that is e to the minus 2x, and then we add c. Of course, we multiply minus 3 half by the whole integral. That means we should have written this way, okay? But regarding the arbitrarity of the constant c, we can write minus 3 half times e to the minus 2x plus minus 3 half c, that we can recall c1. So it is not important because it is only a name for constant. In the particular case, we should have extremal point lower, for instance, lower and upper bound of this integral. So in this case, we should compute the whole integral that you write in this case, in this way, and then multiply everything by this multiplicative constant that is in front of the whole computation of the integral. But in this case, you can write C1, C2, everything that means we have some constant. Okay, I think it is clear. I'm waiting a couple of seconds before changing the board, but I think this is very, very simple. Okay, so let's go further. Why I wanted to write the integral, because this type of integral, because you could have something that you should integrate, and it is important to know that the primitive function of the exponential is not always okay, I can write, I forgot to rewrite. Okay, I'm sorry, it was too loud. Okay, so that means that if we want to perform integrating by part, then we could use, we should pay attention to this kind of integration. So let's integrate by part, but maybe it is better that I choose the next one, because it will be long. Okay. Okay, so let's integrate this kind of function. X third times e to x. Okay. Okay. I will recall very quickly what is the integration by part and why it derives from the product from the derivative of the product of two functions. Someone is writing. Okay, no, it wasn't your chat. Okay, that you know the rule. It is the derivative of the first function times the second plus the first one as it is times the derivative of the second one. Okay, then as you've seen in the theory, if you do the integration of both sides of this equality, that means that you can rewrite everything as integral. That means f times g, the primitive of the derivative of f times g is f times g. And then you can put on the left hand side the integral of f prime times g, and this is a computation in order to obtain some integral that you have in this form. That means you have some function that is easy to derive, that means to differentiate. That means that it is easy to find a derivative of this function, and this should be the function where it is easy to find a primitive of this function, right? Easy to find a primitive G. G is a primitive of G prime, okay? So you have to recognize between this product, in the product of between these two functions, what is f and what is G, okay? So that means that you have something easy to derive and something easy to find the primitive. If you consider the power of x, x to the third power, this is easy to derive because the derivative of this is 3 times x squared. 3 times x squared is something that has a smaller power. So it is something nicer that you can use for the integral. Because if you use x to the third as G prime, that means that you should find a primitive of x to the third that is x to the fourth power divided by 4. And this is nonsense because we have something that is more difficult. I hope that it is clear. So this is in our case f, and this is in our case G prime. Okay, so what does it mean? That we have to find f prime is 3 to x squared, and we have to find G. What is G? Because of the computation before, G is e to the 2x divided by 2, because if we derive G, we obtain 2 times e to the 2x divided by 2, and then e to the 2x as the original term inside the integral. Okay, so let me know if it is difficult, but I know that you always you already seen this kind of computation. It should be okay. Okay, so let's write exactly the formula that I have on the right side. We have the two primitives, f times g. So we have f, x to the third, times the primitive, e to the 2x divided by 2. Okay, minus, now integral of the f, our function x cube, I'm sorry, it is the derivative f prime, of course. The derivative f prime, this is this side. Okay, I will highlight this one because we should use the right one. So this will be okay. Our computation. Okay. So we will have f prime, that is 3x squared times e to the 2x divided by 2 in the x. Okay. Okay, so we arrived by something that it is better than before, because we have the same exponential function, but instead of third power of x, we have a square. We have x squared. So, what is the matter now? We rewrite this integral. So we have x to the third, e to x divided by 2 minus So in this case, we have 3 divided by 2 that we can take outside, or we can let in the integral. 3 half times x squared times e to the 2x. And we can see again this as a product by part. We can see it as a product, and that means that I'm sorry for my voice. Give me a second. So that means that we can again consider these two functions, this product, as a new product that we can consider to integrate by part. What is now our f and what is now our g prime? This is again f and this is g prime, because we can very easily derive this function. So this is 2x, and we can very easily obtain the primitive of g prime, that is g e to the 2x divided by 2. Okay, so that means we can put, instead of this integral, integration by part. So let's rewrite the multiplicative constant outside, minus 3 half, and then write x 2 times e to the 2x, okay, and perform the computation of this single integral on a single step. So let's write maybe in this way. Okay, so let's compute this one. Okay, so what is this? Again, this is f and this is g prime, as I wrote before. Okay, so we have, as this integral is f times g, f as it is, times the primitive function e to the 2x divided by 2 minus f prime times g. F prime is 2x and g is this primitive function, and as you can see it is x. We can we can simplify these two numbers, and then we have x times e to the 2x. So that means that we have again to perform this integral, but in order to have no confusion, okay, we will maybe rewrite everything together. Okay, so that okay equals let's write this one. So, okay. So what is this? This is x third times e to the 2x divided by 2. Okay. This was minus 3 half that multiplies sorry, this integral, but this integral we have this solution, so we have 3 minus 3 half, that multiplies x squared times e to the 2x divided by 2 minus, and now we have integral x to times e to the 2x. So what is, again, f and g? This is f and this is g prime. F prime is 1 because it is derivative of x. And g is, again, e to the 2x divided by 2. Okay, so what is this integral? It is f times g. So x times the primitive again, minus f prime times g. The integral of f prime 1 times g in the x. And now we don't have any more steps, because now we can solve this integral knowing that the primitive of e to the 2x is e to the 2x divided by 2, so that means that we have 1/2 that should multiply the primitive of this integral. So let's write everything. X cubed e to the 2x divided by 2 minus. Now we can multiply 3/2 by the first term in the parentheses, in the big parentheses. So minus 3/4 x squared e to the 2x. Okay. And then we can multiply minus 3/2. We have minus and the first term of this parenthesis. So we have plus 3/4 x e to the 2x. And then we have minus 3/2 that multiplies the last one, but we know that this integral is e to x divided by 4. Okay, so we have a minus. We have again a minus. Minus times minus is plus. That means that if we put minus 3/2 multiplying, it is multiplied by something that is plus. So it remains minus 3/2 e to the 2x divided by 4. Then we can put the constant c that it is a global constant deriving of every computation that we made. We can rewrite maybe, as you see, we have x third, x squared, x and x0, so as 1. We can rewrite everything multiplied by e to the power of 2x because it is easier. So we have x cubed divided by 2. I hope all the computation went okay. But if there is some mistake, let me know. Plus 3/4 x minus 3/8 plus c. Okay, as I said before, plus c means that we have some constant that is not specified, but if we had, and we will see, if we had some particular integral where we should compute lower and upper bound, then we can compute every piece and then put the result all together. I think this is clear, but I can wait a couple of seconds so that you know. It's all right. If you have some question of some something that you notice, but I think it is okay. 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 Okay, so let's perform some other type of integral, and I would say this time we can compute something with upper and a lower bound. So let's give an example. Okay. Okay, with limits, I don't think you had with limits because this was not given in your slides, so I will try to do something without limits. Okay. Yeah, everything with limits. Give me a second. I didn't want to give you limits. Okay. This one. Okay. So the limit between 0 and 4, the integral, sorry, between 0 and 4 of let's write this x fourth plus 1 minus 6x third. Okay, let's begin with something that is not so complicated. Then we will do something with the fractions. Okay, what's this? As you know, the immediate integral of 1 over x, or x to the minus 1, it is the logarithm of the absolute value of x, plus c, of course. Or in the case of the fundamental theorem of the integral calculus, it will be logarithm of the absolute value of b minus logarithm of the absolute value of a. Then you should be aware that if you have some function f of x, as I told you before, in the case of the exponential function, you can write you can write the logarithm, natural logarithm of the function. But as you know, when you derive, when you differentiate this function, you have to write, you have to recall that logarithm of some function. By differentiating, it is 1 over the function, but it is multiplied by the derivative of the function, as every composite function, okay? Because it is the logarithm of another function. The argument is another function, okay? So that means that you should find out if this is the case when this type of a fraction appears. So that means you have to recognize somewhere this function. And this is why we have to compute what is the derivative of the denominator, because it is the function of the denominator, and try to put something in and out as a multiplicative factor that gives us the multiplication by 1 in order to find out if it is the case. What is this? This is 4 times x to the third power and stop, because the derivative of 1 is a constant, it is 0. Of course, you will have x to the third power that is perfectly matching without derivative, but you don't have the right constant. But this is not a problem for us, because we can rewrite, we have minus 6 that belongs already to our integral. And then you have to multiply by 4 and divide by 4, because this is exactly equivalent to 1. This is equal to 1. Okay, now you can rewrite x third, x fourth minus 1 in the x, and then everything that is yellow, this is this type of function. This is this one, okay? This is the right f prime divided by f of x. Okay. What does it mean? That we have to take minus 6 divided by 4, that is minus 3/2, times, what is the primitive function of this one? It is the logarithm of the absolute value of f. What is f? I'm sorry, this was a plus. X to the fourth x to the third plus 1. Okay. And this should be computed. I write the double parentheses between 0 and 4. But sometimes you will find only, as we wrote before, the function and then a straight line, vertical line, and lower and upper bounds on the right side. So, and now you don't need to write down the constant because we have a definite integral to compute. So you have minus 3/2, and then I change parentheses, so that means we compute the primitive function in the first is always the upper, 4 to the fourth, 4 to the fourth plus 1 minus logarithm of 0 to the fourth. Of course, because absolute value, this is something that is already positive because it's an even power of x plus 1, so it is not needed to write down absolute value, because as you've seen, it is everything positive, even if I substitute 0 plus 1. Okay, so that is minus 3/2 times, what is 4 to the fourth? 4 to the third is third is 64. 64 times 4 is 256. That means logarithm of 257 minus logarithm of 1, then it is 0. So this is the result. 257. And I recall that you don't need to write down the constant c because we have definite integral. So this is an example of definite integral. I will write it there. Okay, that means that you have to compute the primitive function, and then compute the primitive function in in the upper bound, and subtract in the lower bound. Okay. Okay, so let's compute some other something that is this one. What I wanted to compute before. Okay, so because this is a simple type of integral, then I wrote down something with e. That I could give you. Give me a second. B. This one. This is an exercise of an exam that could be very useful at of university, where there is again the logarithm. It is not immediate, but we can. I will switch board. Okay, so this kind is very easy to unsee because not always it is clear that the integral of something with a different base for the power is something different. I'll explain. As you know, the derivative of e to the x is e to the x. But for instance, the derivative of 2 to the x, it is not 2 to the x. Okay, I don't know if you know this simple computation, but sometimes you have to handle with other kind of powers, and maybe you could compute this difference. What is 2 to the x? We, as you know, e. Let's explain it with numbers. You always can write some number as a logarithm. Okay, that means everything you can write as e raised to some power that you should give to e, because natural logarithm means base e, that gives you as a result 5. Okay, so this holds always. Okay, it is the same as 3 raised to the logarithm base 3 of 5. That means 3 raised to the power that you should give to 3 in order to obtain 5. This is 5 as a result. So, okay, this is the simple meaning of the logarithm. So, how can you write 2 to the x? You can write it by using the natural base a to the natural logarithm of 2 to the x. But as you know, by the logarithm rules, the exponent of the argument can be seen as a multiplicative factor in front of the logarithm. So this x can be seen as in this new position. That means e to the x times logarithm, natural logarithm of 2. That is a number, as 3, as pi, as everything. So, and if you derive this one, you can consider logarithm of 2 as a number. That means that the function x times natural logarithm of 2, it is seen as a multiplicative factor times x. So the derivative will be the same times the derivative of the function. The function has a derivative 1 times the constant. But, as you know, you can rewrite this one as 2 to the x. So 2 to the x times natural logarithm of 2. So that means that if you derive 2 to the power of x, so you use some other base, you should remember that this factor shouldn't be missing, okay? You should pay attention. Then, if you want to compute the immediate integral, okay, you should remember that it is 2x divided by natural logarithm of 2. Why? The same procedure as before. If you derive this one, you obtain 2x times logarithm of 2 divided by logarithm of 2, that gives you 2x as a derivative. Okay. Okay, so this is the integral I wanted you to submit in order to compute, because not always it is easy to see. This is 2 raised to 1 plus logarithm of x divided by x. In the x. Okay. Or maybe so maybe I can only write this one without 1, because it doesn't matter. 2 raised to the power of logarithm of x divided by x. What is this? Normally, you should find out if you can consider something that it is possible to derive, that gives you this kind of function. And I think you can see this. You can see this this rule if you write one times 2 to the logarithm of x in the x. Okay, 1 over x, I'm sorry. Okay, so we can take the denominator of this function, and we can consider as a multiplicative term that we should consider as what? If you recognize that this is exactly the derivative of the logarithm, okay, what do you have? If you have had e, let's write the two types of integrals so you can see the difference. Let's say that you have before this kind of integral, okay. What is this one? This is e to the f of x multiplied by the derivative of x, because the derivative of the function should be a multiplicative factor a multiplicative factor that is the derivative of e of f, if raised to the power of the function f, as I wrote before. Okay. Okay, so what is the derivative of the logarithm of x? 1 over x. So this is f prime of x. Fine, because you have now to compute only the primitive function e to the logarithm of x. Because the derivative, I rewrite again, but I think the computation should be clear, times 1 over x. Okay? Not plus c, because we have to compute two values of this primitive function. That means that we should compute e raised to the power of natural logarithm of e minus e raised to the power of the logarithm of 1. okay? And that is E, because of the computation before, okay? This is E raised to the power that we should give to E in order to obtain E. So we obtain E minus logarithm of 1 is 0. The power that we shall give to E in order to obtain 1 is always 0. So it is E minus 1. Okay? So let's perform what is above. Above we have not the same Napier number, but we have 2. That means we should pay attention because it is another type of integral. But if we write logarithm of 2, so you could have written logarithm of 2 divided by logarithm of 2 sorry, not e, 2 to the x in the x, okay? This is the same. I'll write in parentheses. This equals. Okay, this is the same. And that means this is the derivative of 2x, as I wrote there below. Okay. Maybe I can. Okay. So I hope this is clear. So let's perform the computation. This is what we should have computed. So we rewrite everything as 2x as you know, we have 2x and not 2 to the power of logarithm of 2, but it is the very same. Maybe I should rewrite this one. Let me cancel. Let me rewrite this. The x. Okay, so I can take some place below. Okay. Okay, so what is the derivative of 2 to the logarithm of x? Okay, it is 1 over x. But the derivative of 2 you can compute in the same way. You have a factor that will come out in the denominator, as in the computation before. The important thing is that you have the logarithm of 2 inside for the derivative, or you divide by the logarithm of 2 outside. That means this is the same as to compute e to the logarithm of 2 raised to the power logarithm of x. That is e for the same reason as before, that is a multiplicative factor of 2, okay? And when you derive, you differentiate this function, you will have, again, everything as it is, multiplied by the derivative of the argument. Now is the function logarithm of x multiplied by logarithm of 2. That means the derivative of logarithm of x is the constant times 1 over x. So that means you have, again, 2 to the logarithm of x. That was what we had before, times logarithm of 2 divided by x. Okay, so this is explained step by step, because then if you want to compute this one, let's write, let's take some color so you won't be confused, I hope. And then some. Okay. Okay. So now the solution is 1 over a logarithm, natural logarithm of 2 times 2 to the logarithm of x computed between 1 and e. So then you have 1 over logarithm of 2, and then you have 2 to the logarithm of e minus 2 to the logarithm of 1. So you have logarithm of 2 as the denominator, so 2 to the power of 1, it is 2, minus 2 of the powers of 0, 2 to the 0 is 1, so it is 1 over logarithm of 2. This is the result. Okay, I hope this wasn't too difficult for you, and I wanted to compute another one because we have time. Let's compute something with with other you didn't have an infinite extremal point, I think, but maybe substitution, you didn't have substitution, but only the rule by part. We could perform this computation. But it is isn't so hard. Yes, maybe this. You you don't have questions, okay? Okay. Okay, let's do another integral. Minus something with logarithm, something with exponential. Something by part. Without substitution. As before, maybe we should recall this type of integral. Something like this one. This is not definite, but maybe it is worth because we should take into account that we can compute the derivative in the same way. Okay, because this is good because I can give you two kinds of steps in order to compute the solution. Minus 1 to the power of 16. I don't know, maybe this could be an exercise of your book. Maybe. Okay. So, as before, this is the same form that we had for the exponential. So, that means that you are in the presence of f of g of x times g prime of x in the x. This is the formula that you were given, I think, equals the primitive of the function f plus c, where you use the chain rule, as before, the chain rule, thanks to this equivalence. Okay? This is the meaning. So you have only to recognize what is the function, what is the argument g, and if there is the derivative of the argument as before. But this kind of integrals maybe is not so immediate, but what is this kind of function? It is the power of something, okay? So in this case, you have that this kind of integral is raising to the power of 16. Raising to the power of 16 means you have a composite function that you should be the derivative of the argument. Okay, so in our case, doing raising the power to 16 if f 16 power. Okay, in our computation. So, what is g? This is g of x. The question is 8x squared the derivative of g? Let's compute g prime and see. G prime is 3 times the derivative of x third. So it is 3 times 3x squared minus 1 is a constant, and its derivative is 0. So it is 9x squared. It is good because we cannot multiply by some power of x. This is not an artificial computation as multiplying by 1. But because we have 9, we could multiply by 9 and divide by 9. That means that this computation is performed by taking 8 times 9 divided by 9 x squared times 3x third minus 1 to the power of 16 in the x. Good. What is the primitive of the 16th power? It is, again, f raised to 16 plus 1 divided 16 plus 1. Okay? As we performed before. So that means this is 8 ninth. Okay, because this belongs to the computation. Okay. This is what is will be the integral. And then we can write the primitive function f with its argument. That means 3x to the third minus 1. 16 plus 1 is 17 divided by 17. Of course, plus c, because we have an indefinite integral. But if you, again, want what you have to perform is something that you can compute in the extremal point of the integral. Last one. Let me choose. Something multiplied. This may be the last one. This is something again that should be in your book, I think, because I have a very long list and I should choose something that is better for us. Okay. What is this? Again, it is a power of log. Okay, now it is a power of logarithm. Okay, and this is tricky because you can compute this by substitution. But I wanted to show you that if you rewrite 2 times x plus 1, this is 1 over x plus 1, the derivative of logarithm of x plus 2. I'm sorry, I said x plus 1, but it was x plus 2. And how do you compute this one? You could recall that the power of logarithm, if you compute the derivative of this one, sorry, square. Yeah, okay, I need the parentheses. Okay, and then you compute the derivative. Okay, this is 2 times 2 minus 1, so the first power of logarithm x plus 2 divided by the derivative of the argument of the power, that is 1, multiplied by the derivative, that is 1 over x plus 2. So it is already something that we have inside the integral. We could compute by substitution, but you didn't do the rule, and now you can recognize this derivative. Only if you don't have to, you can do as the previous integrals, you can multiply and divide by 2. That means write 2 logarithm of x plus 2. Of course, the derivative of x plus 2 is 1 because you had to multiply by the derivative of x plus 2 because it is the argument of the power square. But the derivative of x plus 2 is 1. If you have had 3x inside, okay, it could be, you could have written 3, okay, or something else. So then multiply by 2 above and below means to have 2/4 in the x. That means you have 1/4 times the 2 logarithm x plus 2 divided by x plus 2, that is the primitive function is logarithm of x plus 2 square. And then you add c, or if you have some upper and lower bound, you compute everything. Okay. I think we already had many types of integrals. And let's see if you have some questions. No? You don't have any questions? Something related to what we already did? Okay. So let's then take this exercise to the end. I will upload immediately the slides. I think there are not mistakes in the computations, but if you notice something that are related with some mistake, let me know, write me an email, and I will try to correct them. You should see sharing of the file of this slide that I wrote now in this chat, okay, and it should remains available under the file section. You have everything in the file section in our chat of mathematical tools and methods. Okay, so I think there are no questions. Then I let you know. It could be the same time next week. I'm not really sure. I'll let you know. And for the exercise for next week. So have a nice week. Thank you for hearing today, and bye bye. Goodbye to everyone.
Thank you very much. Bye.
Welcome. Bye. Bye bye.